Hello everyone, I'm Ali and I'm going to present my work on automatic network intent inference. In a typical organization today, the operator is usually given an informal description of how the network should operate, which implicitly defines the networking intents. The operator converts these high-level intents into low-level device configurations, often manually. As a result, there is a significant semantic gap between the high-level intents of operators and the low-level device configurations and network behavior. This gap has been a source of many misconfigurations and network problems that often make news headlines. So there has been a lot of interest and progress towards bridging this gap. Unfortunately, the current approaches in existence today, namely the verification and synthesis approaches, require a formal specification of the high-level intents in order to be able to operate. However, in reality, formal specifications are not usually available. The intents may not be even explicitly known, because as mentioned, intents are usually implicit in informal descriptions, and the operators may even inherit some legacy network from some other operator who has already left the network and are asked to maintain it. In reality, most of the operators are concerned to make changes to their network because they're afraid they might break some existing functionality. In this work, we provide an alternative approach toward bridging this gap. Our idea is to look at the low-level networking forwarding behavior and from that automatically infer the high-level intent. Specifically, we provide Anime, which is a framework and a prototype tool that takes as input a set of low-level observed behavior that is collected from the network through data plane or configuration analysis, live traffic monitoring, or any other means, and as output it generates a set of high-level inferred intents that best describe all the observed behavior. The output can also predict behavior that is possible according to the actual intents but is not necessarily observed during the collection. And there are many applications for such a tool, from input generation to intent-based networking tools to network behavior summarization for human comprehension to misconfiguration detection through anomaly analysis. I'm going to give you a taste of how this can be done through a simple example in which we have a set of user nodes, firewall nodes, and server nodes. If we look at the green arrows, which show the forwarding behavior for the packets destined to 10.0.1.2, if we look at the behavior as shown in the slide, by looking at these together, we can guess that the intent of the operator is to enforce packets destined to 10.0.1.2 that start from a user node to go through a firewall node and ends up in S1. And we represent this guessed inferred intent as shown in the slide. If we repeat the same process with the red arrows, we can guess that the intent is that for packets destined to 10.0.1.3 starting from a user node to go through a firewall and ends up in S2. And if we put these two pieces of information together, we can infer something even higher level, namely that for 10.0.1.2/31, the packet starting from a user node would go through a firewall node and ends up in a server node. This example highlights some of the main ideas used in our work, which I'm going to briefly overview. First, I'm going to introduce our formal framework and use it to formally define our intent inference problem. And then I'm going to overview our proposed solution to it. In our framework, as you saw in the example, each low-level behavior usually corresponds to one concrete forwarding path, and each high-level intent usually represents multiple forwarding paths. In our framework, we use the same formalism to express both low-level behavior and high-level intents. Specifically, we express them through their associated features. Each feature corresponds to one aspect of the forwarding behavior. This can include devices along the path, packet header information, or environmental conditions such as number of link failures or device states. Each feature has a set of labels associated with it that one can choose from in order to describe behavior. And one of the main insights of our work is to take into account the fact that networks are hierarchical, such as in IP hierarchies or the device role hierarchy, as we saw in our example. And so our idea is to accordingly design our feature labels to be hierarchical as well, where at the bottom of the hierarchy we have very specific values, and as we go higher we have less specific values that cover more behavior. We provide a library of different hierarchical feature templates that one can instantiate from in order to express behavior. This includes simple types such as ranges and IP prefixes and sets to more complex feature types such as regular expressions over hierarchical alphabet, the details of which can be found in the paper. And then one can combine multiple features together in a tuple, which itself is a feature template type as well. And this way, the hierarchies of individual features would combine together to produce an overall hierarchy that can be used to express behavior and intents. In this setting, a low-level behavior is a label at the bottom of the hierarchy, and any other label in the hierarchy is a potential high-level intent that can be used to represent a subset of those low-level behavior. And in our framework, we assign a cost to each label in a way that as we go higher in our hierarchy, each label represents more low-level behavior, but at the same time costs more as well. And this setting allows us to formally define our intent inference problem as follows. For a given set of observed behavior and a limit on the number of inferred intents, our goal is to find up to that number of intents that together represent all the observed behavior, and the sum of the cost of those intents is minimized. And this problem as defined here is NP-hard. We provide a heuristic polynomial solution to this problem as follows. For an input set of behavior, we first group the behavior based on their similarity, and then for each group of behavior, we output the single best intent that represents all the behavior in that group as an inferred intent. And we call this the join of that group. In other words, the join of a group of behavior is the least cost common ancestor to those behavior in our hierarchy. And this can be computed efficiently, usually in constant time. And the question is how to do this grouping. And this gets us to our second insight. And that is the cost of the join of a group of behavior is inversely related to the similarity of behavior in that group. For example, joining two user labels is less costly than joining a user and a firewall label. Because in order to represent a user and a firewall node, we have to go higher in our hierarchy and lose more specificity in order to represent both values together in a single label. So our idea is to use common clustering methods to do the grouping, in which we define the distance between two behaviors as the cost of the join of those two behaviors. And we have implemented this idea in a prototype tool and have evaluated it for quality of inferred intents and performance. In this talk, I'm going to focus on some of the quality experiments, and you can refer to the paper for the other experiments. In order to objectively measure quality, we use the precision and recall notions which are used to evaluate machine learning techniques. Intuitively, precision corresponds to the specificity of the inferred intents and recall corresponds to the coverage. And obviously, a good intent inference tool needs to have both good precision as well as good recall. In the first set of experiments, we compared our tool with another tool called net2text, whose goal is to summarize forwarding behavior. We use net2text's own dataset in order to compare the two tools. Our experiments show that for large enough limits on the number of inferred intents, Anime can have better precision than net2text, and in any case, it has about 4 times better recall than net2text. We also evaluated the effect of hierarchical values using synthetic access control policies. In these experiments, we showed that Anime with hierarchical values achieves much better quality results than Anime without hierarchical values. In the experiments so far, we gave all the possible behavior to the tool, and the goal was summarization of those behavior. But we also repeated the experiments with the same dataset, in which we only gave a subset of the possible behavior as input to the tool, and the goal was to also predict unobserved but possible behavior. And again, we showed that Anime achieves much better precision and recall compared to net2text. On the access control dataset, for the optimal values of k, Anime with hierarchical values was able to achieve near perfect FS score, which is defined as the harmonic average of precision and recall. To conclude, we provided a new approach towards bridging the semantic gap by introducing a framework to express network behavior and infer intents. Experiments show that our prototype tool produces objectively high quality results with acceptable performance. Thank you for listening.